In this video, we are going to go over a list of fundamental integrals that are designed to help you in a Calculus 2 class. So let's take a look at number 1. If we have the integral of c times f of x dx, c is constant, and so this is equal to c times the integral of f of x dx. So now notice how I pull c out in front of the integral. Number 2, suppose I have the integral of f of x plus g of x dx. And I'm assuming f and g are both integrable functions. And so this is equal to the integral of f of x dx plus the integral of g of x dx. Let's take a look at number 3. Suppose I had the integral of f of x minus g of x dx. Now again, I'm assuming f and g are both integrable functions. And so this is equal to the integral of f of x dx minus the integral of g of x dx. Now, recall. So, what is the derivative with respect to x of x? So, I claim this is equal to 1. Okay? So, if we think backwards, that says the integral of 1 dx is equal to x plus some constant c. Because remember, the derivative of a constant is 0. With that in mind, let's take a look at number 4. Suppose I had the integral of k dx. This is k times the integral of 1 dx. But look at what we just did. The integral of 1 dx is equal to x plus c. So k times the integral of 1 dx is equal to k times x plus c. That's the rationale for number 4. So let's take a look at number 5. Suppose I have the integral of x to the n dx. This is 1 over n plus 1 x to the n plus 1 plus c. We absolutely have to know this rule for Calculus 2. Now, in this, remember, n cannot equal negative 1. Now, let's take a look at number 6. Suppose I have the integral of 1 over x dx. This is equal to natural log of the absolute value of x plus c. Let's take a look at 7. The integral of e to the x dx is equal to e to the x plus c. Okay, so remember, the derivative of e to the x is e to the x. So the integral of e to the x dx is e to the x plus c. 8. Suppose I have the integral of b to the x dx. I claim this is equal to b to the x divided by natural log of b plus c. Now, for here, b is greater than 0, and then b cannot equal 1, because if b equals 1, natural log of 1 is 0, and we have a problem, because we're not allowed to divide by 0. Okay, let's take a look at 9. The integral of sine of x dx is negative cosine of x plus c. And if you need flashcards or whatever you need to help you remember these, that's fine, right? But the more we can commit these to memory, the better off we'll be. Number 10. Suppose I want the integral of cosine of x dx. This is sine of x plus c. Number 11. The integral of secant x tangent x dx. This is equal to secant x plus c. So remember, the goal is we have to think backwards, because if I take the derivative of secant x with respect to x, I do get secant x tangent x. Number 12, the integral of cosecant x cotangent x dx. This is negative cosecant x plus c. 13, and I'm going to highlight 13. That's going to come up a lot. The integral of 1 over 1 plus x squared dx is arctangent of x plus c. Remember, and this says here, the angle whose tangent is x. So it's the inverse of the tangent. Number 14, the integral of 1 over the square root of 1 minus x squared dx. I claim this one is arc sine x, or inverse sine of x, plus c. Number 15. The integral of sinh x dx. So, by the way, that's hyperbolic sine of x. This is equal to the hyperbolic cosine of x plus c. Now, a couple things to note. Hyperbolic sine of x is e to the x minus e to the negative x divided by 2. Hyperbolic cosine of x is e to the x plus e to the negative x divided by 2. So just a little bit of rationale here. When I take the integral of hyperbolic sine of x dx, what I'm really doing is taking the integral of e to the x minus e to the negative x over 2 dx. Okay. Now I could pull the 1/2 out in front. Okay. And so when I do that, I get 1/2 the integral of e to the x minus e to the negative x dx. Now, here, I get 1/2 of the integral of e to the x dx is e to the x minus, and I claim the integral of e to the negative x dx is negative e to the negative x plus c. But when you subtract a negative, you add. So we get 1/2 of e to the x plus e to the negative x plus c, which is equal to hyperbolic cosine of x, or cosh x, plus c. And that's the rationale for that one. Now, by the same token, you could do the same thing, I claim. If I want the integral of hyperbolic cosine of x, and by the way, that's number 16. If I want the integral of hyperbolic cosine of x dx, this is hyperbolic sine of x plus c. And you could do the same thing, and we can derive it in much the same way. Number 17. If I have the integral of secant x dx, we get natural log of the absolute value of secant x plus tangent x plus c. Believe it or not, this number 17 comes up quite a bit. And then number 18, if I have the integral of f prime of x over f of x dx. So let's make sure we understand this one. And I'm going to do a u substitution. I'm not saying to never do a u substitution, but I'm trying to limit how often we do a u substitution. So I'm going to let u equal f of x. Du is f prime of x dx. And so over here, we're looking at the integral of 1 over u du, which is natural log of the absolute value of u plus c. But u is f of x, so we get natural log of the absolute value of f of x plus c. But I would be happy as a clam in a class like this if we could remember the following. If we get f prime of x over f of x dx, it's behaving like this. It's behaving like 1 over u du, okay? And so it's essentially the chain rule backwards. And we're going to get natural log of the absolute value of f of x plus c. If we can go from here to here, I'm ecstatic, okay? And I want to give you a couple of examples of how this one works. So on number 19, suppose we have the integral of 2x over 1 plus x squared dx. Now, what's the function? The function is 1 plus x squared. The derivative of the function is 2x. So it fits that pattern on the other problem, on the other example. And so here, we're going to get natural log of 1 plus x squared plus some constant c. And I want to give you a couple of others. Let's take a look at 20. Suppose I give you the following. Suppose I give you the integral of f prime of x e to the f of x dx. Well, it's essentially the same idea. I'm going to let u equal f of x. Du is f prime of x dx. And so this is the integral of e to the u du. That's how it's behaving. And so this is e to the u plus c. But u is f of x. And so this is e to the f of x plus c. And so the way I want you to remember is as follows. So we would have the integral of f prime of x e to the f of x dx is e to the f of x plus c. You do that, we're good. I'm happy as a clam. Now, I'm going to give you the same pattern for the next two. If we have the integral of f prime of x cosine of f of x dx, this is sine. So remember, the function whose derivative is cosine is sine. But I'm taking sine of f of x plus c. It's literally how this works. 22. If I have the integral of f prime of x, here, we're going to do this one. Let's do a specific example. I'll show you how it works. Suppose we have the integral of x e to the x squared dx. Now, my function is x squared. The derivative is 2x. But I only have an x, so I need a 2. But I can't just put a 2 without multiplying the integral by a half. Now it fits the pattern, and so what we end up getting is 1/2, that goes along for the ride, times e to the x squared, and then I'm going to add c. So you notice it fits the pattern over here on number 20. Now, let's take a look at number 23. And then we'll call it good on this one. Suppose we have the integral of x squared cosine of x cubed dx. So can we agree that my function is x cubed? The derivative is 3x squared. And then my question to you would be, what's missing? And what's missing is that 3. But I have to put that 3 in so that it fits the pattern. But I can't just put a 3 in without multiplying the integral by 1/3. And so here, my answer will be 1/3 sine of x cubed plus c. And that's 23. Let's do one more for this. 24. Suppose I have the integral of e to the 2x sine of e to the 2x dx. So f of x is e to the 2x. The derivative is 2e raised to the 2x power. So notice how my derivative is missing a factor of 2. So I have to stuff that in. But I can't just do that unless I multiply the integral by a half. Because remember, 1/2 of 2 is 1. And so this is negative 1/2 cosine of e to the 2x plus c. And then let me just, I keep saying it's the last one, but I want to give you the answer to problem 25. So if I have the integral of f prime of x cotangent of f of x dx, can we agree that this is the integral of f prime of x times cosine of f of x divided by sine of f of x dx? Now, I think about the chain rule backwards. The derivative of sine of f of x with respect to x, if we apply the chain rule correctly, we're going to get cosine of f of x multiplied by f prime of x, which is the derivative of that function inside. So my final answer here will be natural log of the absolute value of sine of f of x plus c. Now that will conclude this video. It's a Calculus 2 video where I go over a list of fundamental integrals that you need to know for a Calculus 2 class. Okay, thank you.